I welcome you, all of you, once more. The first is Mr. Rajan Desai. We will be pretty much facilitating the entire fusion presentation. It was his idea to have this fusion presentation. So, Mr. Sippy is an engineering graduate with close to 40 years of experience in field of shell and tube exchangers. He pioneered the technology of rolling titanium tube at the invitation of Babcock, a large-size refinery chain. He developed the proprietary technology on the threaded closer of the Screw Plug Exchanger, which is patented as the Mr. Plug is a very important engineering system and packaging, USL Indian Private Limited. Working since 1977, Mr. Plug has 37 years of experience in acid gas and gas compressor design, includes rotary equipment with specialized working on packaged compressor.
And today, I would like to discuss the most difficult part in shell and tube, which pertains to high pressure, high temperature, and dirty surface. Now, the conventional high pressure, high temperature, the joint, because of the dirty surface, there's always gasketed joints because you need to service them. And when you have these gasketed joints, the bolting can be as large as 6 inches in diameter, and only you need a crane to lift it to be able to pull it. And in the service, how do you open this? And the service, the shutdown periods are very, very limited because you want the plant to run again. So you have very, very limited time. Another method, and that is breech lock, or you call it screw plugs, where the plug is threaded, and that is the one which has to be opened. So that becomes much easier. However, it's not that simple unless you design it very correctly and you manufacture it with equal accuracy. So let me tell you about screw plug exchangers and what they look like. I think this animation will tell you. There's a gasket which goes inside and the tube bundle goes inside. And those are the partition plates. And of course, split ring and things like that. And I'll explain to you a little later what exactly everything is about. And finally is this plug which is screwed in, which you can see is threaded. It looks very simple here. And as you can see, the side of the fasteners are very small and very easy to open in the surface. Normally, the plugs don't open. Okay, this is a sectional view, which this is the tube bundle. This is where your gasket is. This is the shell side fluid here, and this is the tube side fluid. The gasket is here. How is the gasket tight? This is the channel, which is welded to the shell. So there is no opening here. There are no flange here. As a result, the gases are not leaking. They can only intermix. They will be not leaking out. The most important criteria, like in desulfurization and things like that, right? Whereas, so there the efficiency goes down drastically if there is intermix. So this is where we have come up with a gasket which will not allow that. Now, having said that, let me explain what happens with a normal gasket. Now, with the temperature, this, as I told you, is for high pressure and high temperature. refining, is very, not only dirty, it's also corrosive. And this is stainless steel, this is all stainless steel. The reason you can't have this of stainless steel is because allowable stresses are very low with high temperature. As the temperature increases, the allowable stresses go down. As a result, this thickness would be very large to this extent. Very large. These gaskets are not designed for this load. They are designed for your hydro testing and things like that, and that's it. They are not designed for this load at all. So, what happens to this gasket? If I can use that gasket again, I can explain. If you see this gasket, this can be easily crushed because these are just small sheets of metal here, and in between there can be graphite or there can be that problem. So you have a lot of such problems. We also had these problems in the previous year refinery when we had done this job with the specifications. Now, as you see, talking of gold, torque value, 80% of your load goes in overcoming the resistance. Also, as per the acceptance tolerance of manufacture, there is so much of gap between the two. This is a stud and this is your nut, you can say, and the gap is so little, here the gap can be much more. So obviously, here the resistance is much less than this. So if you apply the same torque, you will be tightening some studs much more, the axial load will be much more in some, and in the others, it may not even have any axial load. So what do? You increase the torque. When you increase the torque, you are over tightening some. So that is where your gasket ruptures can rupture. So this uniformity is the most important, and how do you do that? There has to be, you see, doing this in a conventional heat exchanger is quite simple. You can have let's say indicative torque, and the lower side torque, which you tighten everything. Thereafter, just physically see how much your gasket is being compressed. Now, you can easily measure that with an ordinary vernier to see what is the gap between the two flanges. So you have to see the gap between the two flanges is uniform. The procedure is very simple. Wherever with the torque you see the minimum, see that everywhere you get that gap. So that will give you ensure uniformity in time. And the cam profile gaskets are so easily used everywhere to give you that uniformity. I can't reveal that too much, but there is a perfect procedure of seeing that you get this uniform tightening here. And that is because this procedure is quite an exclusive one, and that is why over here most of the companies they use just spiral wound gaskets. And the outcome is in some of the cases there is indeterminacy. Now what happens is this channel in this area is well mounted. Of course, there was an accident in Japan which expelled the whole channel and there were a lot of deaths and a lot of chaos. But that is not possible in any of the designs anymore because we have got threads which are much more overlapping, much more because there is 1 inch, 1 PPI thread and not 3-4 PPI thread or 6. But what happens now is this plug gets seized. As you know, it's a metal to metal contact, and the metals are same. Metal is the same for the plug and the channel. So this bell mounting That means this contracts and this goes up. Actually, what happens is this thread is impossible to move. The cowling takes place because this diameter goes down and this increases, so it gets stuck. There is a certain thickness which is given to the nut, and that thickness is not available without this shrink fit. So we have done the shrink fitting of this ring. It's very simple. We have not allowed the bell mounting to take place at all. We have held down to the bell mount. We have clamped it with this shrink fitting ring. It's very simple to do the shrink fitting. It's like a multi-layer vessel, the way it is constructed, exactly the same way it's shrunk fit. So the plug comes out with utmost ease in our case. We don't have any problem with any of our exchanges so far. There's never been a problem of plug not being removed. If the plug is not removed, then you're just stuck with it and you have to cut it out. This will tell you about this proprietary thickness. Here the channel thickness is this much, here it is added thickness. So the strip lining is done, it's hydrogen disbonding, groove, strip lining. Everything over here in-house. We are heating this with the coils and not with burners to get you uniform heating. And that's how the strip lining takes place. This is the shrink fit ring, which we have to make it very, very accurate so that the shrinking is just the right amount, because there's positive stresses, induced stresses, which are there, which makes the thing all the more rigid. This is the channel which is after heat treatment, so you see this color. And after the heat treatment, after complete welding, heat treatment, and that is the only time this machining takes place, machining of the threads. And we do the threading in the VTL instead of any other horizontal methods of, let's say, a lathe or any other boring machine, because the tool goes down and the gravity is much faster and then it comes up. So all that is not possible when you do the threading on the VTL.
On the life of the thread, is it indefinite or it can be corroded by the so the screw you are making it not be a longer period, or it can be destroyed or corroded something.
See, first of all, there is no fluid coming in there. There is a very heavy duty
High pressure and high temperature.
high pressure. There is a grease which every year we have to lubricate. Yeah, there is a method in which that maintenance is there.
We take more questions later on.
We can take over. Thank you very much. Thank you very much.
Last question on that.
Yeah. Continue. There will be more questions. Okay. Then why? You can run to work.
Haresh sir, like the gasket, is it also patented along with the piece of the gasket, the cam gasket? The cam gasket which you mentioned in the presentation,
Yeah,
that is also
cam profile gasket.
Yes.
We give you space, but we did not see, if you tighten it correctly, you don't see the spares used. Because nothing happens, goes wrong with the cam profile gasket.
Oh, he is asking if it is patented. It is patented by somebody else.
No. You see, the design is patented in this particular case, not the gasket itself. How we use this gasket, the procedure of using this gasket, that's all. This gasket is generally used now, is commonly used now for all the conventional heat exchangers also. Thank you.
For providing such a nice presentation. So I'd like to invite Professor Sami and Sarovaji to this.
Now ladies first.